Hello class, today I want to talk about pH. Uh, this is especially important topic of chapter 6 in our Chemistry 120 class. So I want to do and I think when I lectured on it today in class, I saw some people I thought were really lost. So I want to do it slowly here, and then you can also listen to it over and over again. But this is really one of the major concepts of Chemistry 120. It's also a major concept of Chemistry 180, our General College Chemistry class. So what is pH and where does it come from? Well, it starts with the autoionization of water. So if we have water, water will react with itself, and that will form the hydronium ion and the hydroxide ion. So let's look and see how that happens. Well, this water molecule donates a hydrogen ion to the water. The water in turn becomes the hydronium ion. The loss of the hydrogen ion from this water molecule leaves the hydroxide ion left. So this is called the autoionization of water. Now, you may be thinking, well, how much water actually autoionizes into hydronium ion and hydroxide ion? Well, water is approximately 55 molar. That means 55 moles per liter. The amount of water that actually autoionizes is 1 times 10 to the negative 7th moles per liter. And so that is the concentration of the hydronium ion, and since for every hydronium ion formed, a hydroxide ion has to be formed, the concentration of the hydroxide ion is also 1 times 10 to the negative 7th molar. I'll use a capital N instead of moles per liter here. So the ion product constant of water is a constant that equals the concentration of the hydronium ion times the concentration of the hydroxide ion. So in pure water, the concentration of the hydronium ion is 1 times 10 to the negative 7th molar, and the concentration of the hydroxide ion is 1 times 10 to the negative 7th molar. So if we multiply these two numbers together, remember when you multiply exponents, you add them together, we get 1 times 10 to the negative 14th. And we don't really use the units here. It would be molarity squared, but that unit doesn't have a lot of meaning to us. So 1 times 10 to the negative 14th, it has a specific name along with this constant. It's called the ion product constant for water. And at 20, and this is temperature dependent, so this has to be at 25 degrees Celsius. So at 25 degrees Celsius, the ion product constant for water is 1 times 10 to the negative 14th. So you say, what does this do for me? Well, if we make a little table here of hydronium ion and hydroxide ion concentrations, and we just talked about water having a concentration of the hydronium ion being 1 times 10 to the negative 7th and the hydroxide ion being 1 times 10 to the negative 7th. This is considered neutral. All right, we have equal concentrations of the hydronium ion. I'm just going to say hydrogen ion because that's what it is short. That's equal to the hydroxide ion concentration, we have a neutral solution. Now, if I increase the concentration of the hydronium ion to 1 times 10 to the negative 4th molar, and that is an increase. This is a larger number than 1 times 10 to the negative 7th. When I multiply this concentration times the hydroxide ion concentration, I must get 1 times 10 to the negative 14th. So if the hydrogen ion concentration is 1 times 10 to the negative 4th, and I don't know what the hydroxide ion concentration is, I know that the product of these two must equal 1 times 10 to the negative 14th. So if I divide both sides by 1 times 10 to the negative 4th, I get the hydroxide ion concentration equals 1 times 10 to the negative 14th divided by 1 times 10 to the negative 4th. I get 1 times 10 to the negative 10th. So that is the concentration of the hydroxide ion. Now again, this is less than what it was in the neutral solution, because again, the multiplication of the hydrogen ion times the hydroxide must equal 1 times 10 to the negative 14th at 25 degrees Celsius. So this solutions are solutions where the hydrogen ion concentration or hydronium ion concentration is greater than 1 times 10 to the negative 7th. We consider these solutions acidic because the hydronium ion concentration dominates. We could have something like 1 times 10 to the 0 molar hydronium ion concentration. Therefore, the hydroxide ion concentration would be 1 times 10 to the negative 14th molar. Again, a highly acidic solution. We could also have a hydronium ion concentration of 1 times 10 to the negative 10th molar. Well, that makes this 1 times 10 to the negative 4th molar. Again, when we add these exponents, they must equal 1 times 10 to the negative 14th. We could have 1 times 10 to the negative 14th molar hydronium ion. That means the hydroxide ion is 1 times 10 to the 0. So highly basic solutions. So solutions with the hydronium ion concentration of less than 1 times 10 to the negative 7th, like this and this, are considered basic solutions. All right. So to do these problems, just keep in mind this equation, the ion product constant of water, because that is the equation you use when you know the concentration of either the hydronium or hydroxide, and you know Kw must equal 1 times 10 to the negative 14th, you can solve for the unknown. All right, so you say, what does that have to do with pH? Well, let's look on the next page. So we saw that neutral, I'm just going to write hydrogen ion and hydroxide ion. We saw that at neutral pH, this is 1 times 10 to the negative 7th molar. This is 1 times 10 to the negative 7th molar. Oops. And at basic pHs, we have something like 1 times 10 to the negative 10th molar hydrogen ion, 1 times 10 to the negative 4th molar hydroxide ion. And for things that are acidic, we have something like maybe 1 times 10 to the negative 4th molar hydrogen ion concentration and 1 times 10 to the negative 10th molar hydroxide ion concentration. Well, no one likes to say 1 times 10 to the negative 7th molar, 1 times 10 to the negative 10th. And if you look at the general population does not understand exponential notation. So we need a way of discussing hydrogen ion concentrations in a way that's manageable to the general population. And another thing, if you look at the range of possibilities for the hydrogen ion concentration, we had 1 times 10 to the negative 14th molar, and we have down here in a very acidic solution 1 times 10 to the 0 molar. Well, that's a difference of 10 to the 14th power. That's a large range of numbers. So when we have a large range of numbers, whether it be in chemistry or maybe bacterial growth in biology or population growth, we need a way to express large numbers in a more compact scale. And the way we do that is with logarithms. So just like multiplication and division is the inverse of multiplication, we have a logarithm, and the inverse of it is the exponent. So what this does is, if I have a number that is 10 to the 3rd power, and I take the log of that, base 10, my answer is going to be 3. So log is the inverse of exponent. So log of 10 raised to the 3rd power just gives me the number 3. If I have a number like 10 to the negative 7th power, if I take the log of this, I'm going to get negative 7 for my answer. That's the inverse. Alright, so what chemists came up with is pH. pH equals the negative log, there's the P part, and H stands for the hydrogen ion concentration. So if I take the negative log of 1 times 10 to the negative 14th power, what happens? Well, the log of 1 is 0. You go, how do you know that? Well, if 10 to the 0 power is equal to 1, then if I take log of 10 to the 0 power, I get 0 for my answer, which could be substituted as the log of 1. Log of 1 is equal to 0, because these are equal, right? Okay, so let's erase this so I've got some room. So we were working on taking the negative log of 1 times 10 to the 0 power. So the log of 1 is 0. The log of 10 to the negative 14th gives me a number negative 14. So now my number is negative 14. But we have a correction factor here. There's a negative here multiplied by the negative here, and so we get an answer of 14. So the pH of this solution up here is 14. pH. Let's do this one down here. Well, it would be negative log of 1 times 10 to the 0 power. Negative log of 1 is 0. Log of 10 raised to the 0 power is 0. So we get 0 for an answer here. So the pH for this highly concentrated acidic solution is 0. So the lower the pH, the more acidic. The higher the pH, the more basic. So we could do all of these. This one would be a pH of 10. This is a pH of 7, which is neutral. You've heard that pH 7 is neutral. pH of 4, pH of 0. So now instead of talking about 1 times 10 to the 0 power or 1 times 10 to the negative 14th, we're dealing with the range of 0 to 14. It has taken a large range of numbers and narrowed it down to a range of 0 to 14, which is much more easily able to speak and convey pH. The only problem with the pH scale is this. If the pH of the water you're drinking is 7 and the pH of the coffee you're drinking is 4, how much more acidic is coffee than water? Most people don't understand this. But if you look at this, you know that it's 3 pH units. 3 pH units means 3 factors of 10. So we're dealing with 10 to the 3rd power. Because look at it here. 10 to the negative 7th power to 10 to the negative 4th power. It's a factor of 10 to the 3rd. So coffee is 1,000 times more acidic than water. Juices can even be more. Some juices, like lemon juice, is around pH of 2.5, or let's round it to 2. Let's round it to 3. That would be 10 to the 4th difference between pH of 3 and pH of 7. We're talking about 10,000 times more acidic. This acidity can break down the enamel on your teeth. So after drinking juices or coffee, you should drink water to help neutralize the acid, or at least wash away the acid. So I hope this helps, and if you need more help with pH, let me know, and I'll develop another mini lecture for it. Thanks.